Okay, so we are going now to study what I called previously fractal renewal theory. And this deals with a very simple problem, which is the following. We have the time axis, and we have some events on the time axis. These are called dots on the time axis. And we have some measurement time t. So the total measurement starts at time 0 and it ends at time t. And on these dots, we have some events. For example, the arrival of photons to a detector, or the decay of some nucleus. So these are alpha particles arriving to the detector, or this could be many other things like the jumps of a random walker that occur on these specific times. What we are interested in is the statistics of number of events between time 0 and time t. Later on, this will be used in random walk theory when we have that the number of jumps is not a constant. Up to now, we performed a random walk. The random walk, the number of jumps was fixed. But in real life, if we look at some random walk at some finite time t, then there are fluctuations of the number of jumps, number of times you make steps. And these fluctuations, in many cases, are very important, especially when you have a so-called anomalous diffusion, when the diffusion laws are not normal. So let us define here. We first define the waiting times. This is going to be called tau 1. The second guy is going to be called tau 2, etc. Tau 3. In this case, we have tau 4. And there is also a special time, which is the last time, which is called B. This is this time. It's called B because it's named after, it's called the backward recurrence time. It's the time between the measurement time t and the last event that happened before this guy. So this was the last guy. So of course, you can think about this process also as going on forever, and then there will be maybe another process here. There are also dots on the time axis. So, and these are, we can call them T1, this time here, T2, this is T3, and generally speaking, we'll have here Tn. N is going to be the number of events or renewals in this interval between time 0 and time t. So this event that happens after you finished observing, so you don't really see it, this guy occurs at time Tn plus 1. This n is a random variable. And our question now at the beginning is, what is simply probability to make n jumps in time t? So this is the probability of observing n events in the interval between time t, time 0 and time t. Now, the strongest assumption that I'm going to use here is that the waiting times, also called the sojourn times, there are many names, which are tau I, are simple random variables, are independent, identically distributed random variables. So you generate on a computer, for example, you have some psi of ti, and they are given by common distribution psi tau. Psi tau is a PDF, so it's a normalized function. And now our goal actually is to connect between this waiting time PDF and this PN to see what is the connection. A well-known example is that when psi of tau is exponential, this is written here in units such that the rate is 1. So this is just for convenience. So it looks something like that. This is psi in this example. Then it's easy to show, and we will show in principle, we'll not really go into the details, that Pn of t is given by t to the n, e to the minus t, n factorial. And this is well known, this is called the Poisson distribution. So it depends how long, of course. If you look for long times, you have a probability to have many renewals. If you look for short times, naturally the probability will be to see a few renewals. But roughly speaking, this can look something like, it's on the integers, it can look something like something goes up and then goes down, not as a function of n. And it's discrete. This is for some fixed time t. And it's discrete, that's my point. Pn is discrete, so it's given on these numbers. So generally speaking, it goes up and it goes down, and there is a peak here. Okay, and where is this peak, more or less? It's very obvious. This is the average, more or less. What is the average? It's easy to guess, we will calculate it, but what is the average? The average is, when t is large at least, t over the average time, which is the average here. So when the measurement time t is very long, you have many events, and then roughly speaking, the average is t, the average number of renewals is t divided by the average. And then you have a distribution, Pn of t, and you have a peak, and it's more or less on the average. That's called a regular behavior. That's what you expect. We are now going to consider a case where this is completely wrong. And this will happen when you have a psi of tau is a power law. So we are interested in cases where for large tau you have some power law distribution such that, first of all, the mean, technically speaking, which I think you already know this, is infinite. So there's no average. The average doesn't exist. In this case, we will have a very different behavior. So roughly speaking, this fractal renewal theory is divided into two classes. The case where all the moments exist, that's case one. The case where the average is infinite is case two. There are other cases like when the mean is finite and the variance is infinite, when alpha is between 1 and 2, but we will not treat them. So we will just treat these two cases. When the mean exists, and let's say all the moments of this distribution exist, not this case, we call it the ordinary case, the normal, the standard, then the distribution of PNT is roughly a Gaussian in the limit of large n. So this Poisson distribution will go to something like a Gaussian. But here you'll get something totally different. And now you can, I'll just remind you that this in physics has many applications, and I mentioned one previously. So for example, if you look at the trajectory, this is the position of a Brownian particle starting on the origin. And this is the time t. And you let the particle do a random walk in one dimension. So you look in the microscope, a particle doing diffusion, and you start somewhere. And the does an erratic diffusion, jumping left, right, probability half on the lattice, or taking the limit, Brownian motion. And then you count how many times did it cross the origin. 1, 2, 3 in this example. In this example, again, I'll show this more in detail later. What is the meaning of the distribution of these times? It's the time it takes a particle to start very close to the origin and then come back to the origin, to do this loop. This, we will show later, decays like, so in this example, you have alpha equal half. So you want to know, let's say you are a parent, you are a mother or father, and you live in one dimension, and you decide to let your baby do a random walk. You give him alcohol, and then he does a random walk, so he's moving. You want to know many questions. You want to know, first of all, will he come back? The answer in one dimension is Brownian motion. Yes, he always comes back. What is the average time for it to come back? You see from this answer, the average time is infinite. So it's not good to let the baby just walk without some fence. You can escape to infinity. And then you want to know, let's say you still let him do this. How many times will he come back? These are the type of questions we are asking. So this can be, for example, you have a chemical center, and the particle can diffuse and come back, do something here, can diffuse and come back. You want to know how many times this event occurred. And if it's diffusion in one dimension, these return times will follow a power law. And then you can, of course, you don't need to consider only these dots, how many times you came back. You can consider many, many stochastic variables in this process, which are totally non-trivial and counterintuitive compared to the case where the mean is finite. For example, this guy here is the backward recurrence time. And you can ask, what is the distribution of this time? And for this case, when you don't have a mean, this will scale with the measurement time. So the longer you are, the more big will be B. In contrast, let's say if alpha would be bigger than 1, and let's say all the moments like this B would scale with what? It would be roughly, without solving anything. If you had a finite, if you have Poisson distribution, this last guy, how big is it? Roughly. The average time. So when you have a mean, and it's more general than that, you can prove it. When you have a mean, it doesn't have to be Poisson, it doesn't have to be simple exponential. This B is roughly the size of the average. It can be a little bit bigger, it can be a little bit smaller. For example, if you have, it's obvious, for example, if you have, let's say the waiting times are coming from a delta function. This is your measurement time t, so of course it's a little bit smaller, but it's roughly the size of the average. When you don't have an average, something is replacing the average. What is replacing the average time between events? There's no mean, there's no, that time is infinite, so something has to replace it. What replaces it? T, the measurement time. And that's why this B is proportional to T, and then we say this process is scale-free. And it's a very simple process because it's simply Brownian motion and nothing else. I mean, it's not something very complicated. So now our goal is to do this calculation, and we do it in general, and this is the exercise in probability theory. How do we calculate this? First in general, and then we will consider these classes of distribution. The question at least is well posed. Do you understand what I'm trying to do? It's clear. Okay. So we want to calculate this guy, Pn of t. So how do we do it? What is the trick? The usual trick. We don't want to walk in time, we want to walk in Laplace space. Time is positive, and that's why you want to work in Laplace space. Now, I mentioned already that the waiting times themselves are independent. So you might think this is very similar to summations of IID random variable. But this is not exactly the case because the total time is constraining your process. So tau 1 plus tau 2 plus tau 3 plus b, the backward recurrence time, is fixed time t. So you have some constraint, a global constraint on these IID random variables. And unlike summation of IID random variables, where we fix the number of IID random variables to be n fixed, here n is the random variable. So it's a bit different, but it's still solvable, and we will show how to do this. So our aim is to calculate Pn of t, and we do it soon with Laplace transform. So notice the random variable here is n, while I put here t for convenience. Some people would like to switch them, but never mind. And my first claim is that this is equal to theta tau n t, tn plus 1. And then there is an average, which we need to calculate. What is this theta? So again, recall, you don't need to copy this, is this in your, we had here Tn, and we had here the measurement time, and we had here a theoretical construction Tn plus 1, some event that happened after some time t. So, and here I add n events, for example, 3, whatever. So the claim is that this Pn of t is equal to this average over this theta function. And this theta function called it's like a pulse function. This pulse function is the following: Tn t, Tn plus 1 is equal either 1 or 0. And when is it 1? If the condition is true. What is the if the condition is true? The condition in the parenthesis that if this is true, and otherwise it's 0. It's not clear to me because I'm too long in this business if this is obvious or not, so I'll explain it anyway. Is this obvious? No, why is theta equal, why this? What? No. So let me, it's very simple, but let me explain why. Let us think in an operational way, because actually to solve the problem, once you have this, you solve the problem. It's very easy. The next steps are technical, but it's very, and this is very easy. So why is this theta, why is Pn of t the same as this thing? So, even before that, what are we actually doing? Instead of asking what is the probability that n, you have n events that you count all of them, you say, what is this condition? What is the probability? It's an event that the measurement time t falls between 2 times on the dot axis. Yes, this is what we are doing. We're replacing one problem with another problem. So let's say n in an example, in an experiment, is equal to 3. What do you mean by Pn of t? What is it actually? Well, you are an experimentalist, so God forbid, but let's say, and this is the time axis, and this is my measurement time t. And then I have some renewal, very general. And in this example, I had 5 events, right? So what is, and this is, of course, this is T5. Remember that I'm looking for the condition of T3 and T4. So here I'm going to say theta is equal 0 for this realization. That is a no. The number of renewals was not 3, it was 5, so no. And secondly, the condition is not that t is between T3 and T4, but it is between T5 and T6 in this particular realization. Now I do another experiment, and I have So also here, theta, let's call this experiment 1, this is experiment 2. Also theta here is 0 because the condition is not satisfied because the number of renewals here was 22, whatever. Then you have an example. You continue with this for experimentalists. They repeat the experiment many times. And here we have 3 renewals. Here we are very happy. What is theta here? This is going to be 1. Because you have 3 renewals and the time t is between time t3 and t4. And then we continue like this. Do another set. Here it's 2, theta is 0, and you understand. Then maybe another time you'll have 3 events, and then again theta is 1. And what is Pn of t then? Pn of t is, in this example n is equal to 3, is the sum I from 1 till n, theta I, divided by n. In the limit, n goes to infinity. And what is n here? Not to be confused with this small n. This is the number of realizations you have. That's by definition the probability. So this is the same as the average of theta. So instead of counting each number, I'm just looking what is the probability that.
But it's average on which space?
Now we need to define that. Now we need to, on which space, in the experimental sense, on the stochastic process that I outlined here. In fact, here you can have even correlations, whatever you want. I just said there is some stochastic process, and now we need to understand how to do the average. I mean, I didn't say the average is easy, but we will soon do that. That's not, this quantity is not related at all to assumptions of renewal. We also assume the process started here, that the first guy is the same as the others. We made several assumptions, but this is not important for this general relation. So to find Pn of t for our process, we are going to work with its Laplace pair, Pn of s. And what is Pn of s? It's simply the integral from 0 to infinity exponential minus st Pn t dt. Here we are already doing a theory, so we can integrate from 0 to infinity, even though in experiments we cannot measure up to time t. We are doing a theory, and of course, we want to calculate this guy, and as usual, the usual game, once we have this at the end of the day, you need to do an inverse Laplace transform to go back here. That inverse Laplace transform, as usual, can be a little bit complicated, but it's a technical point. What we'll be able to do very easily is to obtain this guy, and then we can analyze some aspects of this. Generally, to go back is not so easy. And the same happened before when we dealt with the problem of summations with random walks. It's a generic issue. So now to do that, we're going to do, first of all, we are delaying the averaging to the last part. So Pn of s, by this thing, is the integral from 0 to infinity e to the minus s theta function Tn t Tn plus 1, and then I need to do the average dt here. But you see the integral of this function, how does it look like? It looks like a step function. This is Tn, this is Tn plus 1, and this function is 1 or 0. When the condition is holding, it's 1, otherwise it's 0. So this is why we called it before pulse function. And doing this integral is trivial, because we have an integral over some function which is simply a pulse function. So it means that the integration is not from 0 to infinity, but from Tn to Tn plus 1. So what we have here is the integral from Tn. I'll just do it. Okay, we can write it Tn plus 1, Tn e to the minus st dt, and then again at the end we're going to do the average, and then this is equal to, we need to divide by s when you do an integral over an exponential, and then we have e to the minus Tn s minus e to the minus Tn plus 1 s. And still we need to do the averages. So Tn plus 1 is bigger than this guy, so this guy is the smaller number, this guy is all positive, and we are happy. I switched to the order, this guy, because of the minus. Now, this guy is really easy, because it's really easy for renewal, I would say that in the following way. We need to average of over e to the minus Stn and Stn plus 1, but that's the same thing. So what is this, guys? So what is exponential minus Stn average? What is Stn? So I'm going to replace Tn with the taus. So this is the average exponential minus s sum I from 1 till n tau I. For example, in this example, this is tau 1, this is tau 2, this is tau 3, this is T3. So tau 1 plus tau 2 plus tau 3 is T3. So this is, by definition, this guy here is Tn. Tn is a dot on the time axis. Tau i's are the time between renewals. These guys, we assumed, these are the IID random variables. So tau 1 is independent of tau 2, independent of tau 3. That was our assumption. So what do we have here? Just we know that E minus R is some tau generic. What is this guy? This is simply integral from 0 to infinity e to the minus s tau of psi of tau. That's the PDF of tau d tau. And that is nothing else but the Laplace transform of the individual time between renewals. So what we have here is psi of s, one guy, but we have it n times. And in this expression, we have also Tn plus 1. So what would be the difference? Instead of having here n, we will have here n plus 1. So the final conclusion is psi n of s, the Laplace transform of the probability to get n renewals, is simply given by 1 minus psi s divided by s, this is this s, times psi s to the power n, small n. Now, you need to invert it. If you put, you assume, for example, exponential waiting times. So psi of s is 1 over 1 plus s. Then you invert it, you get poles in the complex plane, and then you get the Poisson distribution. This is left for you for an exercise. We're not going to do it. I think that's maybe, there are a few more cases that you can solve this exactly, but most cases you cannot solve it exactly. And what I mean exactly is exactly for short times. By the way, we are not so much interested in short times t. We are more interested in long times, where some generic general features can be seen, and we will come back to this analysis later. Before doing that, I want to do this whole exercise again in a different way, just for you to have a different vocabulary on how to derive these type of results. These are very typical type of results in stochastic theory and renewal theory. So let us do it again with a different language, which might explain to you in a different way what this means.
Why is the averaging on tau?
Why is the averaging on tau? Because think about it as the following. How do you generate the process? You are at this point tau. You are on a computer. Generate tau 1. Then here you are again. Generate tau 2. Generate tau 3. Generate tau 4. But check each time if you are bigger. That's the constraint. So you are averaging obviously on the taus. That's the process.
I understood the average before, but we have experiments, we have
Yeah, but you have to think about this as an infinite number of experiments, and each one of them generated by tau 1, tau 2, tau 3. And what you are generating in the experiment is these distributions of the first guy, which is given by psi of tau, the second guy, the third guy, etc. That's the only thing that you are doing, and that's the only thing you are averaging on.
But the averaging is on n,
No, n is the random variable.
no? So the expectation is...
This is the probability of finding n events between 0 and t. N is random variable. For example, the sum over Pn of S, and going from 0, you can have events where you have 0 renewals. For example, if t is short and the first waiting time falls here, then you have 0. This is equal to 1 minus psi s over s, sum 0 to infinity, psi s to power n. What is this guy? This is a geometric series. This is the same as this guy. This is 1 over s. What does it mean? What is the inverse of 1 over s? In real time is 1. And this means that the sum Pn of t is equal to 1. And that's normalization. So I go back, I didn't understand your question. The random variable is n. This is the random variable that is fluctuating each time. T is fixed. And you have probabilities, and these sum of probabilities give you 1. Okay? So let me derive it in a different way. Might be clearer to you or not. We define Qn and T dt. This is the probability. This is the probability of finding the nth event, nth renewal in t plus delta t. So this t is not the t that we had before. If you want, you can add here some chuk-chik. It's not exactly the same thing. So we just consider the process and have some time t prime here. And then we have some delta t. And we have here all kinds of events. And then we look at the process. And then we count 1, 2, 3. And then we look in this interval. And we ask ourselves, is there an event inside here which is exactly the nth event? Yes or no? The answer is yes or no. Maybe sometimes yes, maybe sometimes no. So for example, if n is equal to 3, then obviously not. So, and then you repeat it again. Maybe n is equal to 3, so here you are lucky, and boom, you add it inside. So here, yes. Here, no. And you do this again and again, and then you can calculate the probability, which I call here probability. N is fixed here. To see the nth event, event number 3, in this small interval. Of course, because delta t goes to 0, this probability is nothing. I mean, when delta t goes to 0, your chances are 0, right? So if you want to measure this, you better take delta t as small in order for something to be inside. Okay, so this is the probability of finding the nth renewal in time in this interval. Now we ask ourselves the following question: what is Qn plus 1 at some time t? So I want to know what is the probability to have the n plus 1 event at some time t, not the Qn. What I'm trying to do is a connection here between Qn and Qn plus 1. If I can connect the two, then you will see I can find this, and then later I can solve this problem. I claim the following, that this Qn plus 1 is the integral from 0 to t, Qn t minus t prime psi tau prime dt prime. This, in my opinion, maybe because I saw it several times in the past, and when you think about it a little bit, it's an integral equation, so it looks a little bit scary, but it's actually very simple interpretation. What does it say? It said the probability that you have the n plus 1 event at time sometime t is the probability that you had it in the nth event sometime previously at time t minus t prime. And then this guy gives you the probability that the time interval between these two events is given by this function that is the input of the model, right? So it's simply that this is, you have here the nth event, here you have the n plus 1 event, and then the interval here is obviously by definition this tau that we had before, that here I call, okay, let's write it as tau, doesn't matter. So this tau, so you had an event here, that there is a probability for that, that is Qn. And then to get the n plus 1, you want an event here, then you need exactly psi tau. For example, if psi tau is 0 in all this interval, then it doesn't contribute. If it's a delta function, it's also easy to understand these things. So this is a very simple relation. It's called it's a recursion relation, actually, because it relates between Qn plus 1 and Q. Now, this type of integral is very common in probability theory. This is called a convolution. And the whole idea of convolutions is that using either Laplace or Fourier or discrete Laplace or discrete Fourier transforms, you can transform this equation to something very simple. We will later deal with one example of convolution theorem. I'm not going to prove the convolution theorem for you. You need to know this. You need to read it. I'll prove it later for some example, one example. But in this context, what we care about is the Laplace transform. So we want to do the Laplace transform of this side and the Laplace transform of that side. And this convolution theorem, this is the convolution theorem of Laplace transform, says the following. Q n plus 1 of s. So s is the Laplace transform of t, the Laplace variable of t, which means simply this is the integral e to the minus st qn plus 1 t dt. Here we have this convolution. So here the convolution, you see the integral is up to t. Here we have t minus t prime, and this, again here t prime, this is equal q hat s of n times the Laplace transform of this. So the magic of convolutions, this is the Laplace transform of the waiting time PDF. So the magic of convolutions is that You have an integral equation, but now you have a multiplication on this side. So it's a very powerful tool. I mean, it's used traditionally, and I'm sure you heard about it somewhere else, or I hope so, in high school. Now, if you think about this a little bit, it's very easy now to solve. All what you need to do is think about what is Q1, because this relation, for example, if n is equal 1, you have a relation between Q2 and Q1. Then you just need to multiply. So if you know Q1, then you know Q2. But what is Q1? That's the easiest thing to do, because we started at time t equals 0, and then we had the first event. This is n equal 1. What is this Qn? Q1 of tau, some tau. This is simply psi of tau. This is the probability that in this small interval, you started here, you will have the event, the first event, by definition. So it follows that Qn of s is simple from this iteration, it's psi of s to power n. All this is very well, but as I mentioned, Q itself is an interesting function, but we are not calculating it directly. We are interested in the probability to have n events. So now we need to think, what is the probability of having n events in time t? How is this related to this function q? This is rather easy, and it is the following. This the integral from 0 to t, qn t minus t prime, times a function w that I'll soon explain, dt prime. So what does it say? We are looking at the time axis. We have many renewals. We have some time t. So we want to know how many renewals are in this time from 0 to time t. We want to know the distribution of this number n. To get n in this time interval, you need to have, before the measurement time, that you have the nth event. And what is this, the probability of this guy? The probability of this event, we said, is Qn some t prime dt. Now, no one cares when you calculate you calculate the probability to have n events. Let's say n is equal to 3. You don't care where exactly is this event. It can be here, it can be here, it can be anywhere. That's why we need to integrate over t prime. Now, we need to do one more thing. We have to be sure that in this interval, nothing happened. No renewal. And that is this function w of t. So this is the probability that no renewal. So your n is actually the last one. No renewal. Took place in 0 t prime. Of course, you integrate over all the t prime, which is the last time here. Okay? And t prime cannot be bigger than t, so this is also obvious. If you had an event, the last renewal was here, this is close to the 0. If the last event was somewhere here, this is related to this integral over t. So now we need to calculate this. Now the point is, what is this w of t? It's the probability that you didn't have an event. And that is related to the probability that you had an event. This is 1 minus the integral from 0 to t, psi of t dt. So this guy is the probability to have any jump, some renewal, between 0 to time t. Remember, this is a PDF, this is a probability, and 1 minus this is the probability of getting nada. So this is this guy. So now, okay, I hope this was clear, and please think about it a bit more, but there are many, many subtleties here. Assuming it was clear, now we need to go back to this equation. And then we look at this equation and what is it? Well, it's a convolution, like before. So what we are going to do is we take the Laplace transform of this. We know we're going to get the multiplication of the Laplace transform of this times the Laplace transform of this. And we know what is the Laplace transform of this guy here. We found it already. But now we need to find the Laplace transform of this guy. That is easy because you are experts. Because when I look at this guy, what is this? This is also a convolution. Bottom line, you have to know convolutions in order to solve everything here. That's the message. So what is the convolution? What is the Laplace transform of this guy? So we have 1. The Laplace transform of 1 is, what is the Laplace transform of 1? 1 over s, simple. And why do I claim this is this is also simple to do the Laplace transform? What is this guy?
1 times 1.
What?
Convolution between 1 and
Exactly. So think about here as a function 1, like this function, but it's 1. So you have a convolution, and then so when I turn it into Laplace, I have 1 times this. I need to take the multiplication of the Laplace transform of 1 with the Laplace transform of this. We said already the Laplace transform of 1 is 1 over s. The Laplace transform of psi is psi of s. So here I get psi of s like that. So if we call this one Aleph, this one we call Bet, and then we use Gimel. So that's the ABC in Hebrew. Aleph, Bet, Gimel. At least you learn Hebrew a little bit. Okay, if you use a Aleph, Bet, Gimel, so what do we get? We get that again, I'm using here the Convolution Theorem on this one, and then I'm just plugging in Laplace transforms. I get 1 minus psi s over s psi s power n. And this is exactly, of course, what I got in the previous method when I used this pulse function, this theta function. So it's the same thing, but just explained in different ways, and I have no clue which is easier. I think they are the same. But some people might like this guy, some might like this guy. These are just languages that people are using in this type of calculations. Yeah, you had a question, or is it?
Why? We said that there is no event between t tag and t, so why is w of t tag is no event between 0 and t tag?
What, you see it here.
I mean, we define w as the probability that no renewal between 0 and t tag, right?
Yeah.
But we want no renewal between t tag and t.
Yeah, but okay, when I said 0, okay, maybe this is confusing. It's not between 0, it's between the last renewal. Okay, took place. Okay, so here, look what you have here. You have the probability of not having renewal after the last event. So it's in all this guy, right? As you say. So, but what is it exactly? It's the probability of not having renewal. You can think about this. Okay, here I start the process from the beginning like this, and now I just don't want to have a renewal. right? So what do you do at this step? You generate from psi of t some random variable, and then it has to fall over here. So it's like starting at 0 here, and then probability of not getting an event up from this time to this time in the process. But here, this is simply in t prime, because I already shifted this process. Yeah. So if you want, this is the same as probability that there's no renewal. No renewal in this language between t minus t prime and t. You agree? But conditioned that you had a renewal because of this Qn on t minus t prime, right? So again, this is the probability of no renewal between t minus t prime in this process. If this is t prime, t minus t prime, and t, but condition that you add a renewal on, so you did have something here. And this is the same as not having a renewal in the original process. You see, the length of the interval is t prime in 0 t prime. Because it's like you started at time 0 and time t prime. So it's simply a shift. Okay? What is the time now? Okay, so we developed the general tools for the calculation of one quantity, that is Pn of S. Soon we'll go for a 10 minutes break, and after the break we will just apply it to different cases depending on the choice of what is the waiting time, what is psi. Okay, so we got this very simple formula in Laplace space for the probability to have n renewals in time interval 0 to time t. Now we want to gain some insight on what is the properties in real time, because, okay, this expression by itself is not so intuitive. So the first thing we want to look at is what is n of t, the average of n of t, when t is large. So again, we have this renewal process. We have here the measurement time, and we have some events, and we are counting them, and then we repeat it many times. We calculate the average, and then we want to know what is n. What is n for short times? That will depend very much on the details of what is psi of tau. So every psi of tau for very short times will have a very specific story to tell you, which might be interesting for this in one context or another. But for that, you need a real model to say something clever. So what we are doing here, we are looking at the long times where we expect that the full details of what is psi of tau are not so important, but only some properties of what are the waiting times PDFs are. So we are going to consider two classes, and that is the case psi of tau. Let's put it like this. With finite moments. An example is the exponential waiting time, which is very familiar, the Poisson process. And especially the first moment exists. E.g., this very simple process. In this case, what do we have in Laplace space? I already taught you that in Laplace space, you have a small s expansion. So by now, I hope that it's kind of clear following the homework of previous lessons that to analyze the large t behavior, what I care about is the small s behavior. Large t, small s, like with k and x, Fourier space, small k, big X, etc. This is, we already studied this, and we call these Tabarian theorems. The Tabarian theorem, we already proved it in a very specific case where we showed that the waiting time PDF, psi of tau decays like a power law. In large times, then at small s, it has a non-analytical behavior. And what we're going to do here is something similar. So what I'm going to claim is, so what I care about is the small s behavior, and the small s behavior of this guy is 1 minus s times the average, blah, blah, blah. The average here is the average time between renewals. This is what we can call this class 1. Class 1 of stochastic processes. Essentially all the processes that have a first moment, I'm implicitly assuming also higher order moments exist, but this is not so important. And we're going to consider also psi of tau, which decays like tau 1 plus alpha. And here, as I mentioned already, alpha is between 0 and 1. So here, the tau average is infinite. And we also showed already that psi of s, small s, behaves like something like a, s to the alpha, and of course there are many more. I mean, example are the one-sided Levy PDFs that have a power law tail. So this PDF, psi of tau is something like this, for example. It has a very long tail. So long that, so fat tail, some people say call it fat, some people call it long, but the mean it doesn't exist. What does it mean actually in reality? Maybe following your homework for this time or next time. If you have some generic PDF like this, what will the dots on the time axis look like? You will find many dots corresponding to the small tau limit of this thing, and then you suddenly see some jump. Then many more dots, and then if you continue this, maybe here many more, but you will see these big gaps where nothing happens. Why do you see these big gaps? Because what is the average time between these events? It's infinite. So what does it actually mean when you generate it on a computer? Is that as you go for longer and longer times, you'll see bigger and bigger intervals with nothing happening inside. So it looks also very non-stationary, and the longer you look, you'll see a bigger gap corresponding to the fact that the time between these guys is infinite. So going back to the Brownian motion case, what you expect is many transitions, then suddenly the particle goes far away in x, then it comes back, and then maybe many crosses many times, and then it goes far away. And these are the big intervals that on this create these big jumps with no characteristic time scale. So again, this is the Brownian motion, where alpha is equal to half. Okay, so we have these two classes. What is important as mathematically, it's either this or this. Of course, in this case, and this case are related. If alpha is equal to 1, then we have s to the 1, and then this a is this tau. What is this a actually? It's related to the amplitude here of decay. So I'm looking at in Laplace space, so a, you can think about it as a generalization of the mean, but of course the mean doesn't exist here. But you see this a has units of time to the power alpha. All this together has no units. So this is a time scale, if you want, which I just call a, which is specific for a distribution. Of course, also tau is specific to the distribution, and also a is specific. So here we have alpha, let's call it this to the power 1. Here we have alpha and a. Here we have only tau. So what happens to the average? So first thing to do is let's calculate the average exactly, but in Laplace space, unfortunately. That's pretty easy. So I want to calculate the average of n in Laplace space. And then all I need to do is I can have, in the time interval 0 to e, I can have 0 events, I can have 1 event, I can have an infinite number of events. I need to sum over all the events, Pn of s times n. That's a definition of the average. So I worked out last lesson, I know this guy, so this is simply equal to 1 minus the Laplace transform of the waiting time divided by s, this guy. And here I have n psi s to the power n, and then I need to do the sum. All these sums are very easy, because if I did not have the n, I already told you this would be a geometric series. Now I have here the n, but there's a very simple trick. What is the trick to calculate these type of sums? Trivial trick. You take the derivative with respect to psi. So if I do that, I take outside everything that does not depend on n. This is this guy related to the what we call w, the probability of not doing anything. And then I will write it d over d psi hat. Then I have psi n. So when I take the derivative with respect to psi, then I have this n, I get it here. But then this guy is going to be n minus 1, right? So I'm going to correct this, and I'm going to multiply everything here by psi of s. And then I need to, of course, do the sum. And the trick is, I'm going to take the derivative outside, and then I have here a geometric series, so it's very easy to do this summation. So it's psi of s 1 minus psi of s divided by s d over d psi, and this is a geometric series from n to infinity. Psi, by the way, is a number smaller than 1 because of normalization. For any s which is bigger than 0, it's smaller than 1. So it's easy to understand that this series converges. And then you have here 1 minus psi of s. Taking the derivative, I get this with respect to psi. I simply get the square of this, and the square of this will cancel this guy. So eventually what I get is psi of s, 1 minus psi of s. And again, this is the average n. Again, in principle, you can take a program, if you know psi of s, then you can invert this numerically if you wanted to on a computer for a specific psi. But let's now assume that we are working with class 1. That is, let's assume that the moments are finite. So again, to look at large t, we need to look at small s. So for case 1, we take s to 0, and then we have the following. We have n of s. We're just going to calculate only the leading term. That's all. So we have here, just plug in 1 minus s, the average tau. Of course, I have many corrections, which I don't care about. S 1 minus s tau, and many corrections that I don't care about. And then you see this guy is small compared to the 1. This is 1 over s. And then I get here 1 over s squared times tau. Plus corrections. If you want to calculate them, be my guest. This will depend on the specific of what is psi is. You need to go further in the expansion. But this guy is very simple. It implies the following. What is the inverse Laplace transform of 1 over s squared? should know this. This is simple. It's simply t. It's very easy to see. You can see this from the units, for example. But you also know this because the answer is very simple. In the long time limit, this is the average number of renewals. Because 1 over s squared, the inverse Laplace transform is simply t. And this is, of course, totally what you expect. We have this renewal process. And you ask how many guys roughly you have here, in an average sense, without fluctuations. Okay, so here I have a mean. This is the average time between events. Then this is obviously going to be t over tau. You know it before, for example, in Poissonian process. The Poisson process, you have some rate. And then the rate is actually similar to 1 over the time between events, and then you will have the rate times t. So for case 2, again we have psi of s 1 minus a s to the alpha. Again we use we use the equation that I just deleted. The equation was psi of s 1 minus psi of s. And again, I use the small s limit. So the leading term is 1. Again, 1, what is 1? It's simply the normalization. There is a small correction, but I'm going to neglect it like before. And here I have 1 minus psi of s. So this 1 is gone. And then this is equal to a s1 plus alpha. And alpha is less than 1. So to invert this is very easy. To the time domain, it's a trivial thing. So I'm just going to summarize. The average of n is the following. It's t over tau if alpha is bigger than 1. And it is gamma function, alpha plus 1 times t to the alpha divided by a. So this and this are the Laplace pairs. It's very easy to go, for example, from here back to here. It's very easy to go. You simply take the Laplace transform of this guy, you multiply by e, s minus st, you do the integral, you'll get this one, and you'll get this gamma function. So please do this. This gamma function is of order 1. It's nothing dramatic in this interval when alpha is between 1 and 2. So this result, one can say it's called in mathematics something like the law of large numbers, essentially. It's the expected result. This guy is also not so surprising in some sense. You can say the following in a hand-waving algebra. Let's say n is more or less, hand-wavingly, is t over the average. Now, what is the average here? This is why I have quotation mark. It's not real average. The average is infinite, right? But what we expect as physicists, maybe not as mathematicians, that this is more or less equal, also this is in the quotation mark, as t. What is the mean here? The mean I want to claim is the integral from 0 to t dt. So I replace this mean with some mean that depends on time. And what do I mean by that? If we have up here infinity, then we have a mean psi t dt. This will be an infinite, and then we'll get nonsense. But because we are looking at some time interval t, then what you expect that the typical time here will depend on measurement time, and then I'm just going to do this hand-wavingly up till time t. Now, if I do that, then this is equal t, the integral. I assumed here this is t minus 1 minus alpha times t dt, integral up till t. This is t minus alpha. The integral is simply t over t 1 minus alpha, and this is equal t to the alpha. So, in some sense, these two guys are similar, or we can understand this intuitively or hand-wavingly. And of course, when alpha goes to 1, then this goes to t. When alpha goes to 0, then you have practically no renewals, and then the number of renewals is very small compared to the ordinary case. However, this mean, while interesting, is not the whole story, because what we would like more is to characterize the full distribution. Full distribution will characterize not only the mean, it will characterize the fluctuations, everything. And recall what I said before, if we have, let's say, a typical case when alpha is greater than 1, let's say Poissonian, then we said that, you know, Pn of t will kind of peak typically close to the mean. And the mean, we now know when t is large is t over tau. And actually one can prove that here in the center you'll have a Gaussian, and these tails can be large deviations, but we understand this picture more or less. This is a generic picture. This will be valid when alpha is bigger than 1, when you have moments, for example, in this case. So we have a very simple picture. But what will happen to the distribution when alpha is less than 1? This will be totally different. And for that, we want to investigate this case. I'm going to do it just to show you that taking the small s limit and then meaning large time, because I care only about large time, is very... it's a powerful method. I'm not going to prove things in a rigorous way, but you'll see that it works. I mean, I'm not going to prove it like a mathematician, because that would take too long. It's actually very easy. What do I need to do? I have this expression. I want to work at large times. I want to work at large times, and I'll do my usual trick. I want to use small s. But I have to take the small s limit in a slightly smart way. So Pn of s is 1 minus psi s divided by s exponential. This is exactly the same thing, of n log of psi s. I'm doing this here because I need to think about this in a scaling limit when n is not arbitrary, not independent of t actually, or not independent of s. Now I plug in the usual expression, 1 minus 1 minus a s alpha. So, of course, there are many corrections. We don't care about them. Exponential n log 1 minus a s alpha, and there are more corrections if we want to work hard. And what we're going to do is we're just going to expand this log. This is the small parameter because we are looking at large times, small s. So this is equal to a s alpha minus 1 exponential minus n a s alpha. This is the expression that we get for s. We actually are going now to try to invert this. When we try to invert this, if you are already experts, you see something. What do you see here? Can any one of you invert this? Try to ignore, let's say ignore this part. So what is this part? This is the Levy distribution, the one-sided Levy distribution. So, okay, you know something. It's related to Levy. And the answer is that the PDF of n of S is related to the Levy, even though we didn't consider sum of IID random variables. We still get your central limit theorem here. It's similar to what I said before, but didn't prove. And this is something maybe you know, maybe you don't. I mentioned before, I deleted it from the blackboard. I mentioned before that if you take the Poisson process, Pn of t which is the Poisson, and you wait for t large enough, the Poisson distribution is like the Gaussian distribution. I hope you learned about this, and if you think about it a bit, you will understand this. And what we are going to say here is that the distribution of n when alpha is less than 1 is related to the Levy distribution. But it's tricky. It's not the Levy exactly that you saw here, you saw before, because the Levy you saw before, you see, what is the random variable? The random variable is n, while this s is for time. So t is a parameter, while n is the random variable. So this Levy distribution will not have a power law tail. It's the inverse Levy distribution. Soon you'll see. There is a subtlety here. But let us forget about this point for a second. Okay, so this is the Levy distribution, but with respect to s, right? With respect to time, not with respect to the random variable n. How will you treat this guy? Do you have an idea?
Derivative.
Yeah, the derivative. So what is the idea? We're going to take the derivative with respect to what? With respect to s. And when I take the derivative with respect to s of this guy, I'll have s alpha minus 1. So I can write this in Laplace space. So again, we see the power of Laplace. So this guy is equal to a d over ds and exponential, actually there's no a here, minus n a s to the alpha. And to compensate, so when I take the derivative, I get s alpha minus 1 and an alpha. So I need to, this is good, the s alpha minus 1 is this guy, but I need to divide by alpha, and I need to divide by n. And I need the minus sign. So this is minus 1 times this. Now, what is the derivative with respect to s, with the minus sign actually, of a function which depends on s in Laplace space? That is easy to show. That is, what is it in real time now, t? It's, you multiply by time t. So going backwards and forward between Laplace, this means that you have to multiply, you have to take the Laplace transform of this function, which is a Levy, and then you need to multiply it by t. We will soon do this, but let me first just write the answer. So Pn of t in this limit, what is the limit? It's t to infinity, is 1 over alpha a 1 over alpha and 1 plus alpha times t. This comes from the derivative here. And the Levy function t over n 1 over alpha And the Levy function is the Laplace pair of E s to the alpha. So you see there is a width here. I define the Levy function L alpha 1, 1 as the inverse Laplace transform of this guy. These are, unlike what is written in my textbook, in my text, in my homepage, these are tabulated today in Mathematica. We assume we know everything about these functions. For me, these functions are simply like Gaussians. They are the kind of well-known. We know many of these properties. We gave it one example at least of this. We know what is the tail of this PDF. The tail of this PDF is t to the minus 1 minus alpha, as you know. But again, look, the random variable is not up here, it's down here. So this whole object is sometimes called the inverse Levy. So this small n corresponds to the tail, if you want it, not the opposite way. So we'll come back to do a little bit of the math, but let's just see how does it look like. Let us assume that we take the limit alpha equal 1. Alpha equal 1 is the boring case where nothing happens. I mean, there's no distribution. Why? What is the e to the minus s? E to the minus s, what is the Levy function? This goes to a delta function, t minus 1. Why? Because you see, if I take the Laplace transform of t minus 1, I get e to the minus s. This will correspond to the fact that Pn of t, if you translate this, if you look at this, is more or less equal in this approximation to a delta function of n is the random variable, minus t over tau. If you want to be more correct, when alpha goes to 1, your distribution goes to a delta function. And this is the law of large numbers. This is what you expect. That fluctuations are 0. If you look, this is actually with a special scaling that you neglected the width of the distribution. So there is a width there, but we actually ignore it. What happens in a more interesting case is alpha equal half. This is an example. We already said this is a nice example because this is Brownian motion. So what is this Levy function? So this Levy function, alpha 1, 1, this was already in the class. And it's given by, it's a normalized distribution, 2 square root of pi, t to the minus 3/2 e minus 1 over 4t. And you see here that when t is big, we get this power law, t to the minus 3/2, which is famous. But this guy cuts it off, so the PDF here looks something like this. This is the one-sided Levy distribution with index alpha equal half. Now what you need to do is you need to insert this guy inside here. You're going to do this. Let's see what will happen. So it looks, if you're not careful, like gigantic fluctuations, but my claim is the fluctuations are actually not so big, and they're actually very simple form. So I'm going to use this equation. Again, alpha is equal half here. So what is Pn of t? goes like this. Alpha is half, so this is 2. And then what do I want to do? Okay. This a is a to the power 2. Then I have t. Then I have n, 1 plus alpha. So this is n to the power 3. And then I have this Levy function. This is 2 square root of pi. This I'm taking from here. Then I have, this is t, this is all this junk now, right? So now this is t a n to the power 2, because here alpha is 2. All this to the minus 3 over 2. Exponential, I have this 4, and then now I need to plug in, instead of t, all this junk. So here I have t, here I have a, n squared. And this will cancel. Let's look at t, for example. Here you get t to the minus half. Okay, so here I'll get t. I'll get a pi. And yeah, it's in the square. I'm looking at a. Yeah, okay. Here is a mistake. Here I have a squared. Is this correct? What's a squared? Yeah, because one second. Yeah,
Maybe there.
Yeah.
Because A and N are the same.
Yeah. Exactly. So here, that's the mistake. Right, here I have the mistake. Here. Good. It's good to do examples. So here I have an 1 over alpha. So here I have an squared. So here eventually I get, okay, this is this t with this t. You get the square root, you get the square root of pi. Here I get a to the power 3 because of this 2, and then here I have a 2, so here I have a and a square root exponential of a n squared over 4t. And remember, here n is bigger than 0, so this is Pn of t. Now, what is this guy?
It's a square.
What?
In the exponential, it's a square on a square.
It's a squared.
Because t is a square.
Yeah. Right, and you see from normalization that this is a because this is like 1 over a squared in the normalization. So here, right? So what we see is something very simple. Think about a as 1. A is not the important parameter here. What is this guy? It's simply a Gaussian. It's something very simple. The fluctuations are not are described by Levi central limit theorem, but they are Gaussian. This is, of course, coincidence for alpha equal half, and because, again, the random variable n here is not up here, it's down there. So sometimes you get a Gaussian distribution, even though it's actually a Levi. It's a bit weird, and you have to digest this, but and in that sense, the fluctuations are not big. I mean, if you look at the variance of n, the variance of n is finite. There's no infinite number of jumps. And this is obvious because the number of jumps cannot be infinity. I mean, it's actually, you have very few jumps when alpha is less than 1. So the fluctuations are not big. They are Gaussian in this case. What is the weird part here? Is let us look at what is Pn of t. So if I plot Pn of t, as a function of n, I want to be more correctly, I'll take n and scale it with square root of t. But it will look, okay, we can do this. You can scale by square root of t, okay, never mind. It will look like a Gaussian, which means that the peak is here. This is for alpha equal half. We said already, if alpha is equal 1, we have Pn of t, you will have something very narrow, which is centered on t over tau. So what happens when all the moments are finite? The PDF, its maximum is close to the average. Where is the average here? The average here is somewhere here. So the average is not representing the most likely event here at all. The most likely event actually is small n limit. N scales with the square root of t to the half. What does this mean? It means that there is a critical alpha where you go from a peak here to a peak there. For example, what happens when alpha goes to 0? It's easy to show that the distribution of n is simply exponential. And what happens if alpha is roughly 0.8? Then I need to take the Levi distribution, I need to plot this. And then I'll see something like something more or less like this. This is a function of n. So what is happening? When I start with alpha equals 0, you have exponential distribution. Exponential distribution is broader than the Gaussian. So as I go up in alpha, from here to here to here to there, I change the peak from the origin, and eventually I go into a delta function, which is a trivial behavior. And depending on alpha, the shape of the distribution is going to change because this Levi distribution, of course, has it depends on this index alpha. Okay? So this is what is happening here. It's not so trivial, but the distribution of n has a limit theorem. There is a limit theorem related to this inverse Levi. However, it changes depending on alpha and the fluctuations. That is, the mean is finite, the variance is finite, everything is finite. All these very typical shapes, I mean, no diverging moments, are all related to actually to Levi statistics. But because the statistics here, it's inverted, you get something with moment, etc. You have any questions on this? I'll leave you guys as an exercise to calculate all there are a few steps that are left, but these are not so difficult. Okay. No questions. I don't know if that's good or bad, but that's the life. What's the time? Okay, so now I want to consider a different topic altogether. תגידי בשתיים וחצי, בסדר? Now we are going to treat usual random walks, no anomalous, no diverging mean. All this stuff is not existing now, and we're going to treat a problem which is called Poison's problem. Poisson was the mathematician who dealt with a very broad class of questions which are called first passage time problems. And the first passage time problem is a very general problem. There are many, many types of questions. One of them is, for example, consider Brownian motion in dimension 1. It can be in any dimension. Soon we'll work in higher dimensions. And we have on x equals 0, let's say we have a molecule A, which is not moving, and my Brownian motion starts somewhere else. And then it starts diffusing, and then it reaches this point at some time t. Or maybe it doesn't. That's actually the question. So this time is called the first passage time. So this is the t-axis. And this first passage time in stochastic process is generally random, because the time it will take this particle to go from here to here will obviously depend on the path. For example, in this path, he went in this way, but let's say the Brownian motion was slightly different and it went the opposite way, it might take him much longer to arrive. So there is a distribution of times which depend on the whole history of the path to come from here to there. And the question is, what is the probability density of this time? How long does it take? What is the average? What is the distribution? That's a first passage time distribution problem. It's related to many things. For example, if here we have molecule, let's say molecule that is sitting here, not moving. For example, some reaction center in your cell, and there's a molecule diffusing, and it has to reach this cell. It does it by diffusion. So it can take a short time to arrive, a long time to arrive. You want to know the distribution of times. But the deepest issue was addressed maybe by Poisson. He asked a simpler question, not when will the particle arrive. That is an interesting question that we will soon address. What Poisson asked is, does the particle arrive? That was the beginning of this research. Does the particle arrive? And he treated random walks. You can think about them as Brownian motion with no external forces, with no boundaries. So that was the beginning, right? Poisson was the first guy. Yeah, he asked the following question. You have a random drunken walker in dimension 1. You have the same in dimension 2. You have the same in dimension 3. And then the question is, you release the guy. Will he come back or will he not come back? And the answer depends, that's what we're going to show, it depends on the dimension. So in one dimension, what will happen? You start here, and if I do a random walk, you will come back with probability 1. Doesn't say anything on how long it will take. It can take very long, it can take very short. Actually, the average time in one dimension, you always come back, but the average time, if you do a random walk in an infinite space, the average time itself will be infinite. But you will come back. In 2 dimensions, similar thing happens. You come back with probability 1, but again, the average time, of course, in 1 dimension, if the average time is infinite, also in 2 dimensions, it will also be infinite. But if you go to 3 dimensions, and you start a random walk, it will have some finite probability only to come back. And there is another probability that it will go to infinity. If the random walk does not come back, we call it a non-recurrent. If it comes back, we call it a recurrent random walk. So what happens in high dimension, it's difficult for me to plot, is that one trajectory might come back. But then you start here, and then the particle simply goes away, and it travels to infinity, and it never comes back to this spot. That's non-recurrent. And when the dimension is very, you can, maybe if you start thinking about it, you can imagine, let's say, you're doing a random walk in dimension infinity, or a very large dimension. So how do you imagine this is, of course, very difficult. But what you think about a lattice. A lattice in one dimension is easy. You think about a cubic lattice. This is a lattice. So you think about a random walk, you jump left and right, you go here, left and right, and then after some time you'll come back. In two dimensions, it's also easy, right? So what is happening when I went to one dimension, I had two nearest neighbors, and you jump to nearest neighbors only, let's say. Now in two dimensions, I have four nearest neighbors. Then in three dimensions, I'll have six, if I do it on a cubic lattice, 6 dimensions, 6 nearest neighbors. And in a high dimension, you will have, of course, many nearest neighbors. So what will happen? You'll go, let's say in dimension 10, you'll go to one of the nearest neighbors. And then from there, the chances of coming back are very small. And then you'll go further, and you will not come back, and you will not resample your origin. So in this sense, you have here an example of what people in physics later discovered in many, many systems, like in phase transitions and other systems, that there is a critical dimension. The critical dimension of this problem is dimension 2. Every dimension higher than 2, you don't return. Dimension less than 2, you do return. I talk about dimension here a bit vaguely, because in physics we can also talk about broken dimensions. If we do the random walk on, let's say, on a fractal object that is not exactly in dimension, which is an integer. But let us now discuss only integer dimensions, 1, 2, 3, which are the most important. 3 is very different than 1 and 2. And also 1 is special, but that is only when you look at the average time of return, not on will you return. This problem and these family, it's a big family of problems. It's very general. There are many, many questions you can imagine with this. First of all, you don't need to do it for random walks on a lattice. That's the simplest example, right? But you can do it when you have external force. You can define the model in different ways, with a force, without a force. And then you can ask, will the particle, when there is a force, will it come back? So for example, without defining too much what I mean by force, but let's say you are in one dimension, and you want to know, you have a particle start here, and the force is in this direction. And what do I mean by force here is the following, let's call it bias. There is a probability to jump left and right, which is not half. It's, let's say, 3/4 to this way and 1/4 to this way. And then you can ask yourself the question, okay, you have a bias to this direction. Will the particle eventually arrive here? And the answer is obvious, yes, because even without a bias, we already said it will arrive. But let's say we start here, and the bias is in this direction. That is, you have some probability to go there, more than to go here. Will the particle always arrive here? This is the first passage time question, where the first question to ask is, with what probability will it arrive here? And the answer is, I'm just telling you the answer, is that when you have a bias in this direction in one dimension, you do not always come back. This is a non-recurrent random walk, because the force, even if it's small, gives you a small probability that you always go in this direction and never come back. Of course, when I say never come back, there is a trivial issue, which is, how do you measure this? So we can define it as a theoretical concept. So in an experiment, maybe you don't want to measure until time infinity. You want to measure until time which is long. So in practice, when we say it doesn't come back, we mean in the theoretical framework where the measurement time is made longer and longer and longer, and when you increase measurement time, you don't see more and more particles arriving. So there is some saturation. After some time, you see nothing is changing. Then you say, okay, they'll never come back. And this is what you do in experiment. And then you can see that in 2 dimensions, particles do come back without bias. In 3 dimensions, they don't. So to treat this very generally, as I mentioned, you can treat this in many games. I mean, you can ask this, for example, in a stock market. You have your stock is going up and down. Let's say you have a model for the stock. It's not trivial to have a model for the stock, but let's say you have a model for the stock. That's the job of economists, to have some models or something like this. And then you always want to know, okay, I invested some money, when will it arrive at some point? Because at that point I want to sell. And you want to know how long it will take to arrive at that point. And that's a random process if you have a random process for your stock. And it can be a zillion other things that describe. So this first passage time distribution is a very big problem because, again, it determines chemical reactions, search problems, many items, not only in physics, but in chemistry, biology, economy, whatever you want. So we do random walks. It's not because they are the most interesting, it's simply because also historically they were the first, and also because we have a knob and understanding what is the stochastic process. And again, it leads you to this dimensionality problem. So what I'm going to consider soon is a discrete time, discrete space random walk. So I want you to think about a lattice, and the simplest lattice is a cubic lattice. So these first passage times I can consider when the space is continuum and time is continuum, or when space is discrete and time is discrete. One of them is discrete, one of them is continuum. There are many variations. So we start with discrete time and discrete space. Discrete time and discrete space, when you first encounter the problem, are the easiest to formulate, let's say, on a computer. So I have here a lattice, let's say in 2 dimensions. And now I'm also going to consider something which we call the return problem. The return problem is, again, a special first passage time problem where the initial condition is where you absorb also. Why do I do this? I don't want to start with some point here, getting here. I'm going to start here and measure here, but this is going to be only a technicality from the point of view of the grand picture. So I start here at time n equals 0. So this is n is going to be time. This is time is discrete. Also, space is discrete because I'm walking on the lattice. Here is the particle. Then I flip a coin. I can jump in this game only to 4 nearest neighbors with equal probability, 1 over 4. And if it would be in 1 dimension, there are 2 nearest neighbors, 1 over 2, 3 dimensions, 1 over 6 nearest neighbors. So only jumps to nearest neighbors to just define the rules. So after 1 jump, I am maybe here. Of course, I could be outside here, 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 etc. Then I again toss a coin. I have time n equal 1 now. This is my, so again, the time is discrete. This is time n equal 1. And then I jump here. And then I might be jumping there. That is time 3. I might be jumping here. This is my path. Boom, I came back. And then I have 1, 2, 3, 4, 5, 6, 7, 8. My first passage time in this path was 8. Now, in principle, if you want to do this exercise, let's say brute force, you just generate all the paths and you need to calculate all their probabilities. That's a hell of a mess. Because, of course, the paths, they can grow because the space is infinite. So what we are going to do in this problem, we are going to relate this problem of what is the distribution of the first arrival time or first passage time to another problem, which you are already experts, and that is how do you propagate on this lattice. So what I'm going to do now, or what is the idea, is we have a problem which is to calculate the distribution of the first time you come back. So it's a distribution where the random variable is time. But what I'm going to use as a tool is the probability to be somewhere in space in x at a given time. So I'm going to relate two problems. What is the probability to be at x at some given time? This is just the solution of the random walk itself. So this you are experts on, quote unquote. You know how to do a random walk in one dimension, a binomial random walk. I assume you know how to solve this without asking the time. You start here, I can calculate these probabilities. Let's say I can calculate them. If I know how to calculate those, I can calculate also the first passage time distribution. And this is a beautiful relation because it says if you know how to propagate this on the lattice, you know something also on the distribution of the first times. This is done through some machinery which is called the Renewal Equation. So let us start with definition. So this is the familiar object for you in discrete time and discrete space. R is the space. So you define a Cartesian coordinate on this lattice. R is the position. R0 is the initial condition. The start of the derivation is very general. It doesn't have to be even to be a lattice. I mean, so we start somewhere, and let us say we know the dynamics, so we know how to calculate the probability to be after n steps at R. Again, this is what you know already from random walk theory. Okay, assume you know it. One dimension. This is the binomial random walk. To a good approximation, when n is large, this is more or less a Gaussian object. That's the central limit theorem if you have no boundary conditions and just diffusion. So this guy is the known, and that is simply the probability of a system being on n, on R, at time, discrete time, n, when we are starting on R0. What do we really want to calculate is Fn. F is from the word first passage time. This is Fn. R0. This is, by definition, the probability of the particle or system visiting R, and this is the important part, for the first time and starting on R0. This is the object that we are interested in. This is the new object. So if I have the probability that you started at R0 and you reached R for the first time after n steps, then I can calculate, for example, the sum of all these guys, when n goes from 1 till infinity, the sum of all these guys gives you what? The probability that you returned at all. Maybe you didn't return. So my claim is, or I'm telling you, or Polyar's claim is, that when I sum all these guys, this probability is not equal 1, because you have a probability that you don't return. The sum of all these guys can be 1. That will happen in 1 dimension. Can be 1 in 2 dimension. But in 3 dimension, it will be some number. And it will also depend on what is the lattice, so what are the jump roads, etc. It will be less than 1 in 3 dimensions. So this is a probability, but it's not normalized because there is a chance that you did not come back. But let's say you did come back. Let's say the sum of these guys is a probability. So the sum over all the n's is 1. Then I can calculate, for example, the average of n. What is the average time to return? That would be simply n, fn, and you sum over n. Or I can calculate the fluctuations, or even better, this will give you the full distribution, the normalized distribution of n. And that will happen in 1 dimension. I can, in principle, if I know this, I know the full distribution of the first time you came back. And this, of course, will depend where you started and where you put your final point. If you start close by or you start far away, it matters, of course. So R and R0 enter here. So the idea is let's find the relation between these two objects. אתה לא נרדם, כי אתה צריך להגיד את זה. The key equation so first of all, just note here that we have some initial condition for P, which is trivial. PR, R0, this is a delta of Kronecker, R0. We are working on a lattice, so at time n equals 0, when you start, the probability of finding the particle, where are you? Where you started. So this is just the initial condition. We will use that a bit later. And now I'll write down the renewal equation, which is the central. This is the central part. The rest is technicalities. So this is the renewal equation. It was derived by some guy in physics. I don't know about math, but in physics it was derived by a guy called Schrödinger. In 1916. So all the greatest physicists like Einstein did Brownian motion, Schrödinger did this, Heisenberg in uncertainty physics, Planck in Fokker-Planck equation, they all were doing stochastic theories because Brownian motion was important. Then there came this quantum world, so they left it a bit, and then, but many of the advances are due to all kinds of clever people. So the renewal equation is a very simple idea when you think about it enough, you are clever enough. It's difficult to do it for the first time, but we are going to look at the probability of finding the particle at position R given that you started at R0. Again, this is what I know already. This is the usual random walk on the lattice. You start somewhere, you end something, you have some probability of finding some particle somewhere in space. Now, the idea is, with one important assumption, but it's a very general idea, that there is a Markovian property of the random walk, which means that once I reach here, the probability to jump left, right, up, down, etc., does not depend on all the history of the path. There is also no time-dependent forces. The jumps are independent of the previous history. It just depends where you are. From here, I can jump up, down, left, right. It doesn't matter where I rolled before in the past. In this case, we're going to claim the following. Let me write it down. J is equal 1 till n, Pn minus j, r, this is not a mistake. So here I have r, and here I have r0. This is the initial condition. Here I have r, and this times fj, this is the first passage, from r, from starting at r0, r. And while there are many technicalities in solving this equation, essentially this is the solution, that's all. But now we, of course, need to understand what it means. So what it means the following. There is a probability to be after n steps at this position. So for example, you are now, guys, you are here. So then let's say there's a probability of you being in this class. Maybe next time it will be 0, but let's say there is a probability that you guys are here. What is this probability that you are here right now? It's related to the probability that you visited this class in the past, and then you did a loop. You came back to this class. Okay? So, and this is more or less what is stated here. What is stated here is the probability that you are in the class is the probability that you arrived here for the first time in some old history, and then you did a loop and you came back here. Let me just try and explain it a bit better with some paths. So the idea is like this. This is a typical path. This is R0. Let's say this is my R. I might have visited this R. This is the final position, but I might have visited this point in the past many times. So to calculate the probability to arrive from here to this point here, it's the same as saying like this. This is a very bad picture. I arrived here, this is the probability I arrived first time, plus now I start here and then I do all these crazy loops up here and come back. So this is what it says here. This is the probability to start at R0, reach R for the first time after J steps. These are the first J steps that arrived here. And then once you arrived at R, then you need to make another loop in what? In the remaining time, n minus j. So you see, here is from time 0 to time j. Here is n minus j plus j is n. So we know this is like, this is the time here is j, and here the time is n minus j. Now, of course, when I go from the start to this point for the first time, this happens at time j, but j can be anything. It can be after 1 step, it can be after 2 steps, it can be of any other step, but it has to be some steps. The maximum number of steps can be n, I mean, because we are looking at Pn, R and R. So this equation, as I said already, is what relates between the probability to find the particles somewhere in space with the initial condition and the first passage distribution. Let us look at this equation. What is this equation from a mathematical point of view? How do you call these type of equations? We already saw this type of equation. How do you solve this equation? So, and when I say solve is assume that we know this. How do I get this? So what is it? What is it? Nearly Laplace transform, but there is no continuous time. But it's a convolution equation in discrete time. Because here I have n minus j. It was like before. We had a function of t minus t prime. And here I have another function of t prime. Here it's n minus j and j. So this is called a convolution equation. This is a convolution, just like before. But it's not convolution in continuous time, it's convolution in discrete time. Why is it in discrete time? Because I define my random walk in discrete time, that's all. So next, we will end here. But the idea is we need to define something which is like a discrete Laplace transform. The discrete Laplace transform is actually called, it's called also a generating function of Z transform. Z transform, generating function. And the generating function is, let's say for P. So like Laplace transform, you take from n to, excuse me, Laplace transform is from time to s. Now I'm going to go from n to something called z. So z and n are pairs. If you want here, we can have a hat of r0. This is a sum of n equals 0 to infinity Pn r0 z to the n. This, if you think about z as e to the minus s and n as like t, is very similar to the Laplace transform. This might be a bit obscure for you right now, but I'm telling you it's very similar to Laplace transform. We're going to use this, we're going to define the same for f. Then we're going to be able to express f in z space exactly. Then we need to solve, of course, that's not easier said than done, we need to solve this Pn. Let's say for random walk on some lattice. And then we are able to, if we can invert, we can then find this Fn in the time domain. So the bottom line is, and this we'll do in the beginning of the next lesson, the bottom line is that we have a very simple, well, it's not so simple, but we have a relation between the probabilities of being somewhere in space with an initial condition. The loop, here, this loop is very important. I can put here, if I want to do the return problem, I will put here R0 equal R. I can start somewhere else. So this is a very general equation. It can deal with many things. While I discussed here a little bit this cubic lattice, you understand that this is a general equation. It's not related to random walks on lattices. It can be, let's say you put the lattice in a finite space, or you have a different graph, or you have biases. This type of equation is very general. It only assumes that the history is not important. So the idea is, I arrive for the first time from here to here. I don't care what is the path, how I arrived, to determine the probability of coming back. So this probability here didn't depend on the full history. This return probability didn't depend on what was the path in the whole history. This is, again, this Markovian assumption, but this is a very this is a very general assumption that the random walker or the particle will not recall all its full history backward in time. So it's a huge class of random walks, or stochastic processes more generally, that satisfy this renewal equation. Again, we can define it in discrete time like we did here. We define it in discrete space like we did here. But we can do the same in discrete time, in continuous time, for example. And then this sum will just turn into an integral over time. And we don't want to do this, but it's possible. The discrete time, discrete space is, again, very easy because you generate times, and then the first passage time is very clear when you land back at the point you wanted to. So discrete time and discrete space, while maybe annoying from point of view of notation, from conceptual view of when you exactly, what is the meaning of coming back is obvious. The reason why I'm saying this, consider Brownian motion, which is a continuous path. To come back to a point might be a difficult concept for you guys. Because what is exactly to come for the first time to a point which has measure 0? So on a lattice, it's easier to understand when you come back to a given point, because I think it's very straightforward to understand. But on a continuum trajectory, which is a random trajectory, it's a bit more subtle. Okay, so I'll see you guys next week, and that's it, I guess.